This video is brought to you by mywayteaching.com.
So in this part we are going to study about temperature dependence of resistivity. Okay. See, the resistivity of a material is found to be dependent on the temperature. So temperature and resistivity are interdependent. Different materials do not exhibit the same dependence on temperatures. Obviously, it depends on various other factors also. So, some materials behave differently with temperature. Okay, which means they exhibit different dependence with temperature, different kind of dependence or different amount of dependence with the temperature. Okay. Over a limited range of temperatures that is not too large, the resistivity of a metallic conductor is approximately given by, it is given how it is dependent, it is given by this equation. So this rho T is the resistivity at a temperature T, and this rho naught, it is the same at a reference temperature T naught, resistivity at temperature T. And this rho naught is resistivity at temperature, reference temperature T naught. Okay. And this alpha is the temperature coefficient of resistor. Okay. Temperature coefficient, and the dimension of alpha is given by T raised to minus 1. For metals, this alpha is positive, and values of alpha for some materials at T0 is equal to 0 degrees Celsius are listed in table that we'll see now. So here the relation between this equation or whatever this equation is, describing, it implies that a graph of rho T plotted against T would be a straight line. There is a linear dependence. At temperatures much lower than 0 degrees Celsius, the graph, however, deviates and considerably form a straight line. As you can see in this. So here the graph of rho T versus T, you can see it is a one graph, and the straight line graph is here, the graph of rho T against temperature T. Okay. At temperatures much lower than 0 degrees Celsius, it deviates, considerably deviates from a straight line. You can see. This is for a typical semiconductor. So here at above 0 degrees Celsius, it is a straight line. Below that, it deviates from a straight line. And here this is a temperature dependence of resistivity for a typical semiconductor. Some materials like nichrome, which is an alloy of nickel, iron and chromium, they exhibit a very weak dependence of resistivity with temperature. You can see this is the graph. And manganese and constantan, they have similar properties. So here, these materials, they are widely used in wire-bound standard resistors. We already saw that that winding of wire of alloy, we produce that wire-bound resistors. And here the resistance values would change very little with temperature. Okay. Unlike metals, the resistivities of semiconductors, it decreases with increasing temperature. You can see it here. So it decreases with increasing temperature, isn't it? And we can understand that the temperature dependence of resistivity in the light of a deviation, it is the resistivity of material is given by rho is equal to 1 by sigma, that is m n e square tau. So rho is thus dependence inversely both on the number n of free electrons per unit volume, and even it is inversely dependent on the average time between collisions tau. So as we increase the temperature, average speed of electrons which act as the carriers of current increases, resulting in more frequent collisions. So the average time of collision thus decreases with temperature. And in a metal, this N is not dependent on the temperature to any appreciable extent. This N is not at all depending on the temperature. So the decrease in the value of tau with rise in temperature causes rho to increase. For insulators and semiconductors, this N it increases with temperature. So this increase more than compensates any decrease in tau, so that for such materials rho decreases with temperature. So for metals it is different, and for semiconductors and insulators here it is different. Okay. Now let us see one simple example here. An electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, its resistance at room temperature is found to be 75.3 ohm. When the toaster is connected to a 230 volt supply, the current settles after a few seconds to a steady value of 2.68 amps. What is the steady temperature of the nichrome element? The temperature coefficient of resistance of nichrome averaged over the temperature range involved is 1.7 into 10 raised to minus 4 per degree Celsius. So this is the question. We should find the solution for this question. Okay. See, when the current through the element is very small, heating effects can be ignored and the temperature T1 of the element is the same as room temperature. Okay. When toaster is connected to the supply, its initial current will be slightly higher than its steady value of 2.68 amps. But due to heating effect of current, the temperature will rise. That will cause an increase in resistance and a slight decrease in current. In few seconds, this steady state it will be reached when temperature will rise no further, and both resistance of the element and the current drawn will achieve steady values. Okay, so in that case the resistance R2 at steady temperature T2 is given by is given by R2 is equal to 230 volt by 2.68 amps, which is equal to 85.8 ohms. So using the relation that we know, that is R2 is equal to R1 1 plus alpha T2 minus T1, we know this equation, isn't it? And this alpha is given by, in the equation they have given the value of alpha 1.70 into 10 raised to minus 4 per degree Celsius. So here we know R2 and R1 value. So T2 minus T1 is equal to R2 by R1 minus 1 into 1 by alpha, isn't it? So this, in other words, we can write R2 minus R1 by R1 into 1 by alpha. So T2 minus T1 is equal to R2 is 85.8 ohms, R1 is 75.3, and alpha (1.70 into 10 raised to minus 4). So this gives us the value of 820 degrees Celsius. Okay. T2 minus T1 is equal to 820 degrees Celsius. So we know the value of T1, that is 27, which gives 847 degrees Celsius. Okay, the steady temperature of the heating element is 847 degrees Celsius. Moving to another example. The resistance of the platinum wire of a platinum resistance thermometer at the ice point is 5 ohm, and at steam point it is 5.23 ohm. When the thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohm. Calculate the temperature of the bath. Okay. From the data given, we can make down the values of resistance. R0 as 5 ohm and R100 is 5.23 and RT is equal to 5.795. Okay. So RT is equal to R0 1 plus alpha T. So here we want T, which is given by RT minus R0 R100 minus R0 into 100. Okay. And we know the resistance values. Which is given by 345.65 degrees Celsius. This is the value of T. Okay.